Now we have to introduce some extra constraints so that this truth assignment has to be satisfying. And to do that, we're going to introduce a set of nodes for each clause that is sometimes referred to as a gadget. These gadgets come up a lot in NP completeness proofs. In this case, it's going to be a little piece of a graph, but it's going to be a little piece of a graph that has particular mechanics to it that makes the graph act like a three-sat problem. All right, now we're going to extend this graph by adding a gadget for each clause. Now, gadget is just going to be a little chunk of a graph, but it's going to have very particular property to it, that it's going to be three-colorable in the context of the rest of the graph if and only if the corresponding clause is satisfiable in the context of the assignment. So let's imagine that we've got, this is our clause, L1, L2, L3. All right, so there's a couple different ways of making this gadget. Here's one that makes sense to me. Essentially, there's going to be little triangles that kind of correspond to OR expressions. And the OR of L1 and L2 ORed with L3 is going to give us the answer for the clause. So here's the 6 nodes. They're going to be connected to some of the nodes that are already in the graph. In particular, the 3 literals that are in the clause, and the slack variable in the middle, slack node in the middle, and the false node off to the side. And just to simplify things, remind you that the false node is colored black, the slack node is colored red, and these literal nodes are either going to be blue or black, each one. And now what I'd like to do is show you that the different ways of coloring these either allow the rest of this structure to be colored with 3 colors or not. So let's start off with the case where all 3 of the literals are false. That's an important case because if the assignment is such that the literals are all false, then it's not satisfied. This clause is not satisfied, so the whole formula is not satisfied. So this is going to be important to make sure that this graph is not going to be colorable. So given that these 2 nodes are connected to slack, neither of them can be red. So this one in particular can either be blue or black. If this one's colored blue, then that means neither of these can be colored blue, and neither of these can be colored black, so they have to be both colored red, and that doesn't work. So this can't be blue, and it can't be red, so it has to be black. These can either be blue or red, it doesn't matter which is which. All right, so now we have this node. Oh, well, this node is kind of obvious. It's connected to red and black, so it has to be blue. Now this node is connected to blue and black, so it has to be red. And this node is connected to red, blue, and black, so we are in trouble. So the graph was not colorable when these 3 literals are all black. What if this literal is blue? Well, that means that one of the literals in the clause is true, so the whole clause should be true, so this better be colorable. Okay, by the same argument before, this is red and black, so this one has to be blue as well. So it looks like we're okay. We're able to assign colors to all these nodes so that none of the coloring constraints are violated, so that's okay. So if this one is blue and these guys are black, actually this one doesn't matter what it is. The thing is colorable. What if this one were, so this could either be blue or black. What if this one were blue? Well, that's going to be okay too, because we can just swap the 2 colors of these nodes. All right, so what that means is if this one is blue, the thing is colorable, definitely. So one of them is true. This one is true. That's enough. So let's consider the case where this one's black and one of the other guys is blue. All right, so this one's forced to be blue. Since this one's black and this one's blue, this one's forced to be red, which means this one's forced to be black, which means this one's forced to be blue. And now we're in good shape because this one's black and this one's red, and now we have a valid coloring. Actually, no matter what, L2 is colored. And the same argument works if we switch which one of these 2 is blue. We can just swap these 2 colors and everything's fine. So what did we just show? So this gadget for this clause is colorable as long as the 3 literals it's connected to are not all black. And that's great because that's exactly what the satisfiability condition is. So we create one of these gadgets for each of the clauses, connect them to the rest of the graph, and now we get this giant graph. And that whole graph is satisfied if and only if all the gadgets can be colored, which is the same as saying if and only if all the clauses can be satisfied. And since they're all connected with ands, that's exactly what we wanted it to be. So this graph that we've built is colorable if and only if the entire formula is satisfiable. That's kind of cool, Right. So even though a formula with Boolean variables in it and a graph with different colors in it feel like very different problems, in a very deep, fundamental, mathematical way, they're really the same problem.